In this video, we begin our discussion on thermochemistry. Thermochemistry is the study of energy flow during chemical transformations. This is a very crucial area, very important to understand and to be able to harness energy flow during chemical transformations. And before we begin, this graphic illustrates some of this importance. What's shown here is the world primary energy consumption as a function of year from 1950 to 2050. This was generated in 2017, so of course the 2017 to 2050 years are simply predictions. And it shows that there's large amounts of energy produced by oil and biofuels, as well as coal and biomass and natural gas. And these are all chemical transformations. All of these involve combustion. So we're looking at energy flow during combustion processes and harnessing that energy flow to do work. Solar is also shown on here, and solar energy involves photophysical and photochemical processes as well. And you can see that oil consumption appears to be peaking around the time that we're working at right now. But it's important to be able to understand all these processes. And so in order to do that, we're going to need to look at the various forms of energy and their interconversion. And then we're going to look at a term called enthalpy. Enthalpy is a property of materials, and it's very useful for understanding heat and the ability to do work. Then we're going to look at calorimetry, which is the experimental measurement of heat flow during chemical processes or during physical transformations like phase changes. We'll move on to stoichiometry. And so this is our last expansion of stoichiometry this semester. This is going to take us to the most complex level. We're going to need to understand stoichiometry of chemical reactions, and then we're going to apply thermochemical principles to that stoichiometry. So we'll not only understand mass flow, but we'll also understand heat flow. Then we'll look at something called Hess's law, which allows us to calculate delta H for a variety of different processes. And during this, we'll look at what are called standard enthalpies of reaction. To begin, thermodynamics is the study of energy and its transformations. There are thermodynamics courses in the physics department and in Parks College. So the engineers study thermodynamics, as well as a number of other scientists. Thermochemistry is what we're going to focus on, and that is a branch of thermodynamics, a small subset that deals with the heat flow during chemical changes and also in physical changes. When energy is transferred from one object to another, it can appear as work or heat. Now we have a few definitions we need to work on because it's very important to properly define the system that we're looking at. So a system turns out to be the contents of the materials that are under study. So that might be the reactants in a chemical reaction or material that's undergoing a transformation. The system is anything in that reaction. And then we have something called the surroundings. That's everything else. That may include the container. That can sometimes include the solvent in which the chemical reaction is occurring. So for example, if you're looking at a precipitation reaction, we think back to chapter 4, we remember learning about precipitation. You can take lead salts, iodide salts. We react them, we get lead iodide. Lead iodide may be the reaction that we're looking at, but the beaker, the air above the beaker, the entire surroundings of the lab, all the instruments that we're using, and even the solvent can comprise these surroundings. So our system are the chemical materials that are under study. And we'll see that pretty clearly as we go through and do some practice problems. The surroundings, that's the rest of the universe. You can think of the universe as an infinite sink and an infinite source of energy and matter that's available to our system. There are a couple of types of systems, and we're going to focus on what are called closed systems. In a closed system, no matter enters or leaves the system. So it's a sealed container or a sealed reaction vessel. Now, the vessel itself may not be sealed, but we don't have any of our reactants or products exiting the vessel. Now, open systems are more complex. These are ones in which matter can move into or out of the system, so the systems and surroundings can be exchanging matter. And those are more complex cases. But they're simply extensions of closed systems with respect to thermodynamics. Now let's define some quantities. E will be very important to us. It's called the internal energy of a system. That's the total energy of a system under a given set of conditions. That includes the kinetic and potential energies of all the particles. We'll see later that we may not actually be able to quantify what the internal energy of a system is absolutely, but we can develop relative scales where we can tie things to references and then determine precisely what the energy of a particular system is relative to a standard. There are a few types of energy flows that happen during processes. One is heat. So heat is given by the letter Q. So Q is the heat absorbed or released by a system during a process. So we'll see that in general, heat is not a property of a system so much as what occurs during a process. And work, likewise, work is not a property of a system. It's what happens during a transformation. So W we define as work done on or by a system during a process. So now E can be defined for a system in a particular state, but a system will not have a Q or a W. During a transformation, moving from one state to another state, E will change, and so we can label that delta E. That would be E final minus E initial. And during that process, the energy change of the system will be equal to the sum of the heat plus the work that happened during the process, moving between state 1 or state 2. If delta E is positive, the internal energy has gone from the surroundings into the system. If delta E is negative, the internal energy from the system has gone into the surroundings. So the system plus the surroundings equals the entire universe. The internal energy of a system is the sum of all the potential and kinetic energies of all the particles, as we said before. And we may not know the absolute value for these, but we can tie them precisely to references. And then we'll be able to know with good certainty what the energy change would be going from one state to another state, which is what we're concerned with. The total energy of the universe remains constant, which is another statement of the conservation of energy. A change in energy of the system must be accompanied by an equal and opposite change in the energy of the surroundings. So, like we said before, not only is the system plus the surroundings equal to the universe, the energy of the system plus the energy of the surroundings equals the energy of the universe, which is a constant. Here are diagrams to help us visualize these transformations. So on the left-hand side, we have an energy level diagram. So the vertical arrow, energy, shows energy increasing. And the green box, the initial state of the system, that's the starting condition of your system. That might be the reactants in a chemical reaction. They're at the energy state E initial. So they're in that energy state. And after the process occurs, the chemical reaction is complete, then we have our final state of the system, which is the brown box on the bottom. That might be the products of our chemical reaction, and they are at the energy state E final. In this case, we see E final is less than E initial. Therefore, delta E is less than 0. E final minus E initial will be a negative value. Energy has been released into the surroundings, and that may be handled as heat or as work, or some combination of those two. So this is a case in the left-hand side where the energy of a system has decreased during a process. On the right-hand side, we see the opposite process. We have our initial energy state is lower, and the final energy state is higher. So the green initial state is given at E initial. Our final state is E final. So E final minus E initial will be a positive value. Therefore, energy has been absorbed from the surroundings. Two quick examples, and we'll go through a lot of these later on. The first on the left-hand side might be a combustion reaction where biomass, say a tree log could be burned and release energy into the surroundings. On the right-hand side, we might have photosynthesis, where a tree absorbs sunlight from the sun and converts carbon dioxide and water into biomass. So delta E is E final minus E initial. So we see we're going from an initial state to a final state. Therefore, delta E is the final minus the initial values. So we've said that delta E is the sum of Q plus W. We'll consider two cases. In the first case, we'll consider W to be 0. So now we're looking at heat only. Therefore, delta E will equal Q. So on our left-hand side in this case, we have our initial state is at a higher energy, and our final state is a lower energy. This would correspond, for example, to having hot water that cools down and releases heat into the surroundings. One thing to notice here, if we had a closed system, which is what we're generally going to work with, we wouldn't be, and water was our system, we wouldn't have steam escaping because that would make it an open system. So we'll probably have a sealed container here or something with a lid on it to prevent the water vapor from escaping to the atmosphere. And the heat flows out of the water into the surroundings. So our energy state is higher at the beginning and lower at the end. So now delta E is Q, and that's a negative value. The system has cooled. On the right-hand side, our initial state is at low energy. Here we might have water and ice mixed together in some equilibrium mixture. So it's a cold system. If we set it in a warm room, then it will heat up to some final state. And as it heats from E initial to E final, heat is absorbed from the surroundings. So in this case, E final is greater than E initial, delta E is greater than 0, Q is positive. System warms. So if we have only heat transferred in a process, if delta E is negative, then Q is negative. That's when our system is cooling down. If delta E is positive, that is Q is positive, then the system would be warming. Next, let's look at work. There's a variety of types of work. Of course, there's gravitational work, electrical work. We're going to focus primarily on pressure volume work. And in our first semester, that's all we'll look at. We won't really look at other types of work. Pressure volume work occurs typically when a gas is released or absorbed during a chemical reaction. So here we have two cylinders. And inside the cylinder is a gas, and that forms our system. You can see on the left-hand side we have our initial state. There's a system that has a pressure inside, and of course that pressure equilibrates with the atmosphere. And so the inside pressure is equal to the outside pressure. We have an equilibrium state. But now during some transformation, we see that the volume of our system has increased. Delta V is a positive value. What happens here is the system has expanded. When the system expands, it pushes back the atmosphere. Therefore, the system is doing work. And so we write this down as W equals minus P delta V. So work is minus P delta V. In this case, delta V is positive, so the work is negative. And we'll see examples of this. We'll look at a case here where we have no heat transfer. We only do energy transfer via work. So now delta E is equal to W. Q is 0, and W is equal to minus P delta V. We're just doing PDV work, what we call PDV work. Pressure times change in volume. On the left-hand side, we have our initial state of the system, and the initial state of the system is at higher energy. So we have a reaction. You can see there's a dark powder at the bottom. It's reacting and releasing bubbles of gas. Those bubbles of gas then push against the atmosphere, and they do work against the atmosphere. Our final state is lower than our initial state, therefore delta E is negative, and work will be negative. On the right-hand side, we have the opposite case. Our initial state is lower in energy, so E initial is lower. And this might be a case where gas is absorbed by reaction. So, for example, calcium oxide can react with CO2 to absorb it to form calcium carbonate. And so as we absorb gas, then the atmosphere does work on the system. So our final state is greater than our initial state, so delta E now is positive. Therefore, W is positive. So let's write these out. For the first case, delta E is equal to W equals minus P delta V. V final is greater than V initial. This is the expansion case. Delta V is positive. If delta V is positive, minus P delta V is negative. Therefore, W and delta E are negative. The system does work. In the second case, V final is less than V initial. Therefore, delta V is negative. So minus P delta V overall is a positive value. So delta E and W are both positive. Work has been done on the system. We'll go through example cases when we get to the mechanics for this chapter. You'll need to practice this when you go to your ALEKS homework, and we'll see how we keep track of signs. This is a very important thing. So here are our sign conventions. We have Q and W and delta E. If Q is positive, the system has absorbed heat. If W is positive, the surroundings have done work on the system, then delta E will be positive. If Q is positive and W is negative, or if Q is negative and W is positive, the overall value of E, delta E, will depend on the sizes of Q and W, whether it's positive or negative. If Q is negative and W is negative, that is, if Q is negative, the system will release heat. And if W is negative, the system has done work, then delta E will be negative. Now, this is taken from your textbook, and there's a little bit of language you probably want to be careful with. At the bottom, Silverberg and Amateus have written down Q is positive, means the system gains heat. Heat is a process-related function, as we'll see in a moment. So we have to be careful not to think of a system as containing heat. It may contain enthalpy, as we'll see later on, but that is something that is a little bit different. So it's important to differentiate that here. You know what we call state versus a path function. And let's start on the bottom first. I know we have a top definition of path function, but let's start on the bottom with state function. This might be easier to understand to begin with. A state function is a variable or a property of a system which only depends on the state of the system. It doesn't depend on how you got there. So, for example, the pressure of a system. That's a measurable, and it's simply a property of a system under a given set of conditions. It doesn't matter how it got there, the pressure will still be the same. If you measure the pressure, that's the correct value. Pressure, volume, temperature, internal energy, number of moles, those are all state functions. They are properties of a system under a given set of conditions at a given state. And we'll see later on H, which we haven't defined yet, which is enthalpy, is also a state function. Up above are path functions. Path functions depend on how you move between two states. So a simple example might be you walk from your dorm room to a lecture hall. The distance you travel is a path function. There are multiple ways to get there. Your altitude altitude change between your dorm room and your lecture hall will be a state function because those are always the same. How long you took to get there and the distance you traversed are path functions. Other important path functions in chemistry are work and, in general, heat. Here's an example of how this might be done. So we can think of C8H18. We learned the name for that compound in our earlier chapter on chemical naming. That is octane. So octane is one of the primary components in gasoline, and octane can undergo combustion. So we see another energy level diagram here. The green box is octane plus oxygen is our initial state. This can undergo combustion, so we can burn octane to produce carbon dioxide and water. So the brown box at the bottom is the final state. So we see the energy change here. Is delta E positive or negative? Delta E is negative. So in this case, though, there's two different ways that we can do this combustion. We can do combustion in an open barrel, so you can maybe take 10 gallons of gasoline, put it in an open barrel, light it on fire, and you'll see lots of light. That's a form of energy. We'll see lots of heat given off. There is a little bit of work pushing against the atmosphere, but it's not productive work. Alternatively, we can put this into an automobile and do our combustion in a controlled manner inside an internal combustion engine. In this case, we do get some heat release, but we also get productive work, moving a car down the road and driving all the systems within the automobile. So here's two different processes. The same internal energy change has occurred for the octane going to carbon dioxide, but the amount of heat versus work will depend on how we do the process. So that's the difference between a path function and a state function. E is a state function. The energy change of the material, the octane, will be the same, but what we get out of it, whether it's just heat or whether it's heat and work, will depend on how we do the process. The direction you take in walking from your dorm room to your lecture hall can be very different. If you take a very long circuitous path, it will require more time and energy on your part. But the change in your state in the end will be the same. You'll end up in the same locations. Here we have the law of conservation of energy, and this is one to always remember. We've discussed this before, but we need to understand that delta E is always conserved for the entire universe. So the delta E for the system plus the delta E for the surroundings will always equal 0. This is a restatement of our previous graphs that we saw, figures. If delta E for the system is positive, then delta E for the surroundings will be negative, and the magnitude will be the same. If delta E for the system is negative, delta E for the surroundings is positive. Again, the magnitude will be the same as well as the sign. Next up, we have our energy units. We'll concern ourselves quite a bit with this when we get to the problem-solving portion of Chapter 6. Our primary energy unit we're going to use is joules. Joules is based on the SI units of kilograms and meters and seconds. Calories used to be an important unit, but are not used nearly as much. And then finally, there are British thermal units, and BTUs are sometimes used by engineers, but we'll focus on joules in this course. And the scientific unit of joule is the one that is predominantly used, and going forward, that's really the one that's used in the future. That's based on universal standards. Now we're going to turn our attention to a property called enthalpy. Enthalpy is a very important parameter. It's given the capital letter H. And we'll see that this is the property of substances that you'll find in tabulations. So these are very important numbers that are used in government and industrial and academic labs to quantify energy changes and transformations in systems. Enthalpy is defined H as equaling E plus PV, where E is our familiar internal energy and P are the properties pressure and volume. So H is simply E plus PV. There are reasons why this was defined this way. Josiah Willard Gibbs and a number of other thermodynamicists developed these quantities to address behavior of engines and chemical transformations. So now we have H is equal to E plus PV. These are all state functions, it turns out. E and PV are state functions. H is as well a state function. And we can do transformation. And so we can go from one state to another state. So start off an initial state, go to a final state. So we can have a delta H, a change in enthalpy. That will be the enthalpy of the final state minus the enthalpy of the initial state. We'll do quite a few problems with that later on and see how that works out. Now, if we have a delta H, then we would have a delta across our other side of our equation. So we have delta E plus delta PV, which expands into delta E plus P delta V plus V delta P. So here's our equation. Delta H is delta E plus P delta V plus V delta P. Now we know that delta E is equal to Q plus W. Forgive that there's a equal sign missing there. That equal sign will be correctly articulated in your lecture PowerPoints. And work is equal to minus P delta V. Remember that. And at constant pressure, so if P equals a constant, V delta P is 0. If P is a constant, delta P is 0. Therefore, the product V delta P is 0. So we can now plug these values in. So for delta E, we can put in Q plus W. For W, we can put in minus P delta V. And for V delta P, we can put in 0. And if we do that, we see all the following terms cancel out. So now we see something that's very curious. This is a very important concept right here. This is a key concept. It's one that Over the years, a lot of folks have difficulty with this concept when they first encounter enthalpy, but this is a very simple way to think about this. Enthalpy is heat at constant pressure. So we think of enthalpy as being related to energy and having similar properties, but in the final analysis, enthalpy can be thought of as heat at constant pressure. Now this is important. We just said before that a material does not contain a heat, but it does contain or have an enthalpy as its property. And under constant pressure conditions, which is what lots of our lab conditions are, heat and enthalpy can be identified as related to one another. So now heat at constant pressure becomes a state function because it is equal to enthalpy. Delta H sub P, enthalpy at constant pressure, is equal to Q sub P, heat at constant pressure. Now, enthalpy is generally more than this, but this is a great way to think about it, and this will be the way for you to think about this, because this is the way chemically that we will use this throughout this course, and we'll also do this in general chemistry 2 and in physical chemistry, and when we have laboratories, when we do, when we have energetic materials, for example. We do processes and we concern ourselves with Q sub P, or enthalpy. It's very important. So we're going to conclude our lecture here, and then our next lecture will continue on with a discussion of enthalpy and a lot more details on this very important parameter.